This video has been made possible by Wandrium. What is your address? Not just your house number or the name of your street. Where, actually, are you? In a town or a city which is in a country, on a continent, on Earth. But where is Earth? Why, it's in the solar system between Venus and Mars, you might say. But where is that? The solar system is the main part of the Oort cloud, a vast collection of comets, asteroids, and icy objects swirling at the fringes of the Sun's sphere of influence. The Oort cloud resides in the local interstellar cloud, which is in the local cavity of the Orion arm of the Milky Way galaxy. The Milky Way is a spiral galaxy with beautiful, sweeping arms of millions upon millions of stars, all rotating around a bright galactic core with a dark, supermassive black hole at its center. At over 100,000 light-years across, the Milky Way is vast, but it is still just a sliver of what we can see. Zoom out further and you'll see a local group with 30 to 50 small galaxies and a monster on a collision course, the Andromeda Galaxy. Twice the size of the Milky Way, Andromeda is speeding towards us. We will collide in a few billion years, tearing each other apart before coalescing into one. But when you zoom out even further, the impending collision of two galaxies seems inconsequential. At the scale of millions of light-years, the structure of the Virgo Supercluster, a collection of thousands of galaxies, becomes apparent. And dwarfing even that is the Laniakea Supercluster, hundreds of millions of light-years across, containing several other superclusters like our Virgo, and which is itself part of the Pisces-Cetus Supercluster complex, a galactic filament almost a billion light-years long. And it is now that the cosmic web becomes visible. There are more filaments like our own, as well as great strings of superclusters. There are also giant stretches of space with virtually nothing in them. Like the Boötes Void, an area 330 million light-years across in which we have discovered barely 60 galaxies. An ink blot on the speckled sky. Zooming out further, we finally reach the edge of the observable universe, where primordial light has been traveling since nearly the beginning of time, 13.8 billion years, to reach our eyes. But since then, of course, the universe has expanded further, meaning that the true distance to the edge is about 46 billion light-years in one direction, meaning the full observable universe is a sphere 93 billion light-years in diameter. Structures any larger than a few billion light-years are hard to define with our current technology, partially because we are trying to map something we inhabit, and partially because there may well be a limit, something scientists call the end of greatness. But at every level up to this point, planets, solar systems, galaxies, clusters, superclusters, the universe is full of structure. It is not a random and chaotic jumble. It seems organized. Yet the universe started as a hot, dense soup of particles. Why should it now be structured? Why did that hot soup evolve into a universe where some parts are filled with beautiful, sweeping arms of stars, while others are barren deserts? And more importantly, how do we know? How did we start this channel? To begin with, a lot of research and in-depth exploration of the universe's first moments. And a huge part of that was done through Wandrium, the educational subscription service. And I'm not exaggerating. Wandrium used to be called Great Courses Plus, which made university-level lecture series, and they've now expanded to contain even more content. From travelogues and tutorials to long-form documentaries, Wandrium is now the best place for all your high-quality, enjoyable content that is guaranteed to make you smarter. One great example of this is Sean Carroll's peerless lecture series, Dark Matter, dark energy. I am currently on my third listen through, and I learn something new each time. 24 half-hour cosmology lectures given by the best science communicator out there. For example, it really helped me understand the reasoning behind the theory of inflation. Just superb, and only one of many other courses on offer. I'm not exaggerating when I say that without Wondrium, this channel may not have existed. It is the best educational subscription service out there, and they're giving viewers a great offer of a free trial. So get the fantastic education I did by heading over to wondrium.com/history of the universe. Thanks to Wondrium for supporting education on YouTube. The year is 1502, and Nicolaus Copernicus should be studying medicine in Padua. It is the center for medical education in Europe. All the best teachers and students gather there to learn how to heal the sick. But Nicolaus is a polymath. He is learning medicine, but he's also reading Aristotle and Plutarch and Plato, and finding holes in Ptolemy's theories in his spare time. Finishing his degree, he returns home to Poland to work as a physician for his father, though he doesn't forget about the cosmos, or our place in it. And so, it is a decade later that he writes a pamphlet outlining his now ubiquitous theory. We are not the center of the universe. The Earth orbits the Sun, just like all the other planets. We are not special. Nicolaus knows the uproar this will cause, so he doesn't publish right away. It is only in his 70th year, some say it's actually on his deathbed that he approves the final copy, that the book finally comes out. And it shakes the very foundations of science, astronomy, philosophy, and religion. An idea so dangerous and fantastical that its proponents would be persecuted for decades after its publication. The heretical notion that our Earth is just the third planet among many. At the time, it was a shocking thought, but it marked only the beginning of a larger revelation. For if we are just some planet orbiting a random star, what does that make us? Not special. It's a sad realization at first, but when we think deeper, it opens up a world of possibilities. If we are not special, what else is out there? Who else is out there to discover? Known as the Copernican principle, the idea is now a bedrock of modern cosmology and has two related tenets. The Earth is not special. We don't occupy some privileged position in the universe. Therefore, observations from the Earth should be relatively representative of observations from anywhere. One modern-day discovery that backed up this claim was the detection of the cosmic microwave background, or the CMB. A fuzzy background static, it permeates the sky, no matter in which direction you look. No matter how powerful your telescope, if you keep zooming in on a part of the sky with nothing in it, you will still detect faint microwave radiation, always with almost the same wavelength. Emitted at a time close to the beginning of the universe, at the moment when matter cooled down enough for protons to capture electrons and become clear gas, it is everywhere. In this regard, our bit of the universe is clearly not special. Outer space, no matter which direction you look, has a temperature of about 2.7 degrees Kelvin. It doesn't matter if you are floating in outer space near the Milky Way or past distant Methuselah, the average temperature of empty space is about the same. But there is an obvious issue with this, and one that doesn't require a high-powered telescope to recognize. Our cosmic address is full of huge structures. Galaxies, superclusters, great walls of stars hundreds of millions of light years across, and great voids with nothing in them. The universe clearly isn't totally uniform. We aren't special, but there are structures. All large-scale structure in the universe can be explained by two opposing forces, expansion and gravity. The universe started hot and dense, and then underwent three phases of expansion. The first lasted a fraction of a second and was extreme. This is called inflation. It then continued to expand in a second stage for several billion years at a more reasonable rate. cooling down, spreading out, and slowing its expansion. And in the last few billion years, it has entered a third stage, in which expansion has accelerated again. And so what is responsible for these shifting regimes of expansion? The initial inflation has been theorized to have been caused by a mysterious field called the inflaton. The latter expansion, a mysterious energy so baffling it's simply known as dark energy. In truth, we don't know for sure, but what we are sure of is the existence of gravity, which has spent billions of years battling against the quickening expansion. When a part of the early universe became a bit denser, that overdensity attracted more matter, which consequently made it more massive, and so gravity acted even stronger to bring more matter in. Clouds of dust and gas became stars, which clumped into galaxies, and so on. It was and is gravity doing what gravity does, at its most basic level. Problem solved. But not quite. Because you can't start this process with a totally even universe. Just where did the first overdensities come from? The best answers we have now started to be revealed with space telescopes in the late 1980s, and the race to map the entire universe to higher and higher resolution. The Cosmic Background Explorer, COBE, was launched from Vandenberg Air Force Base in Southern California by NASA in 1989. The Cold War was ending, and a new era of cooperation between global superpowers was about to begin. And what better way to start this new era than the first baby picture of the universe? COBE had a bold mission: take detailed images of the entire celestial sphere and tell us how uniform the background radiation really is. And so on April the 24th, 1992, the results were plastered on the front page of the New York Times. Scientists report profound insight on how time began. COBE had mapped tiny variations, anisotropies, in the cosmic microwave background radiation. They were very small, just 1 part in 100,000, but they were there. This blockbuster result won 2 Nobel Prizes in 2006 for 2 of the lead astronomers on the telescope, John C. Mather and George F. Smoot, with the Nobel Committee marking it as the birth of cosmology as a precise science. The success of COBE led NASA to launch another telescope in 2001 called the Wilkinson Microwave Anisotropy Probe, or WMAP. This further proved the blockbuster capabilities of space telescopes, and instead of a vague smear of under and over dense regions, WMAP was able to tell fine structure, and patterns started to emerge. So again, in 2009, the Planck satellite was launched by the European Space Agency to get an even better picture of the baby universe. Each successive experiment kept demonstrating the same principle. There were tiny fluctuations in the very early universe, which, after being stretched out by expansion and clumped by gravity, led to the structures we see today. And there are dozens of other experiments, telescopes, and satellites, each discovering and mapping new parts of this structure. Back on Earth, one of the best telescopes for mapping the universe is the Sloan Digital Sky Survey. Perched on a mountain in New Mexico, this telescope creates a map of the whole sky in an unusual way. First, the astronomers take a regular optical image. Then, they create an aluminium plate with a precise hole drilled for each star or other astronomical object in the image. They then run a fiber optic cable from each of the holes in the plate to spectrographs, so they can find the colors of the stars and therefore find out how far away they are and how fast they're moving. These rainbow-collecting aluminium plates are each custom-drilled and capture a unique slice of the universe. So far, over 10,000 plates have been drilled. By combining data from different surveys, astronomers managed to define Laniakea, our local supercluster. Home. A group of thousands of galaxies all bound together by gravity. And our universe maps are filled with many more fantastical places. Of course, stretching out from our own local group of galaxies is the Virgo supercluster, whose tendrils connect into the Centaurus supercluster. Beyond that is the Perseus-Pisces supercluster and the South Pole Wall, which stretches across over 1 billion light-years. And the Sloan Great Wall is about 1 billion light-years in the other direction, an equally mammoth structure. And some astronomers believe that the Milky Way and a large part of Laniakea actually reside within another supermassive void, known as KBC, proposed to be almost 2 billion light-years in diameter, though its existence is still hotly debated. And even these have been dwarfed by a recent discovery. The giant arc was discovered in 2021 and is about 9 billion light-years away. It is thought to span 3.1 billion light-years, 3.5% of the observable cosmos, and is so huge it actually challenges our assumptions about the universe on the largest scales. If you zoom all the way out, a pattern appears. Filaments tie together into walls and clusters with large voids hanging between them. But what is the structure of this web? Is it like meatballs of matter in a soup of emptiness, or pancakes of matter arranged at jaunty angles? Surprisingly, answering this seemingly ridiculous question, which kitchen metaphor does the large-scale structure of our universe most resemble, would obsess the field of cosmology for decades. Truth, pride, and Nobel Prizes were at stake. At the largest scales, is the universe like a meatball soup, a honeycomb, or a sponge? A grizzled veteran of the Soviet atomic program sits in his office in Moscow, contemplating the universe. How did the large-scale structure of the universe arise, he asks himself. Perhaps his contemplations make him hungry for lunch. On the other side of the world, a mild-mannered Canadian sits in his office in Princeton, contemplating the universe. How do tiny particles become huge galaxies? Similarly, hunger-inducing thoughts. So perhaps he wanders down to the cafeteria for a break. The name of the astronomer in America is Jim Peebles. He would eventually win the Nobel Prize in Physics in 2019 for theoretical discoveries in physical cosmology. He and others of the American school believed that matter in the universe was organized like meatballs in a low-density soup. Matter would attract matter, which would attract more mass, clumping together in roughly spherical assemblies, leaving vast areas of low density. This was a bottom-up approach. The large-scale structure gets formed by clumping smaller-scale structures. Meanwhile, behind the Iron Curtain, Soviet astronomers were busy developing their own theory. Yakov Zeldovich was the Russian musing on the cosmos. By the 1970s, he was a renowned physicist who had cut his teeth in the Soviet nuclear program before turning his attention to the large-scale structure of the universe. He had developed a theory where the density in the universe was organized in 2D pancakes, and where the pancakes overlapped, you would have galaxy formation. In this way, the large-scale structure comes first, and galaxies are formed from them. In Zeldovich's universe, there are large empty voids with filaments on the edges of pancakes and clusters where pancakes intersect. Zeldovich was a brilliant scientist with a lot of sway in the Soviet Union, but because of his role, he was rarely, if ever, permitted to leave the USSR. His ideas therefore took longer to disseminate than they might have otherwise. And so at the height of the Cold War, you had Jim Peebles, a soft-spoken Canadian living in the USA, advocating for a universe dominated by meatball clumps, and the Russian school, led by a hardened veteran of the Soviet atomic program, believing in the pancake model. Meatballs versus pancakes. There's no evidence of animosity between the two, but without hard data, each stuck to their own beliefs. But luckily, between them was an unlikely interloper. Martin Rees, an English astronomer who would one day become the UK's Astronomer Royal. He acted as a sort of go-between for the American and Russian schools. The English were more permissive about which meetings they were allowed to attend than either the Americans or the Russians. And so, Rees's postdoc, a man from Kentucky named Richard Gott, then developed a third theory that better matches the findings of later experiments, like the Sloan Digital Sky Survey. Gott met Zeldovich at a conference in Estonia, then part of the USSR, in 1977, and this meeting, along with developments in observation, would lead to a new understanding of the universe. As recounted by Gott in his book The Cosmic Web, Zeldovich was a character. "Always use the median," he said. "In Russia, the watches are not made very well, so when friends get together, they compare the times on their watches. One says 5 minutes to 5, another says 5 o'clock, the other says 11 o'clock. Use the median." Inspired by the brilliant Soviet, Gott would develop a new theory. The universe is like a sponge. The topology of Gott's universe lies conceptually between the American meatballs and the Russian pancakes. According to him, high-density and low-density regions are connected and complementary. In other words, you could switch high-density for low-density and it would be the same. As new maps like those from the Sloan Digital Sky Survey became available, this is the structure that was observed. Neither meatballs nor pancakes, but a sponge. But this is not everything that our telescopes have seen. As our methods of scanning the skies have improved and we have seen further and further back in time with increasing detail, something strange has been observed. A phenomena referred to by some as the end of greatness. At around 1 billion light-years, the universe finally becomes homogeneous, the same everywhere. Large-scale structure disappears. Why? Imagine you are in Ecuador, standing on the equator. Look up in the night sky with a powerful telescope and observe the cosmic microwave background radiation in all of its majesty. Take a careful measurement of its temperature. Now fly to Indonesia, on the equator, on the exact opposite side of the Earth, and look up. If you take a careful measurement of the temperature of the CMB, you'll find it matches the measurement you took in Ecuador. The light from each point took about 14 billion years to reach you, meaning the points would now be 28 billion light-years apart, except that space has been expanding in the intervening years, so they're really much farther away than that. And yet, the universe is only about 13.8 billion years old. To put it simply, there hadn't been enough time for the light that you saw in Indonesia to have reached the light you saw in Ecuador. So how could they possibly be the same temperature? How could they know what temperature to agree on if they couldn't thermodynamically talk to each other? Perhaps it's a coincidence, so you pick 2 other random points in the sky. They will also match temperature to within 1 part in 100,000. This is the horizon problem. When you look at the microwave background radiation, it is extremely uniform. When you look at colorful images from experiments like WMAP or Planck, the color differences are deceptive. The differences between red and blue are actually tiny. They are differences of 1 part in 100,000. For almost all intents and purposes, that's the same temperature. And so this poses a fundamental physical challenge. And it is one of the reasons for the development of the idea of inflation. The theory, proposed by Alan Guth in the 1980s, is that there must have been some very rapid expansion in the early universe. With inflation, parts of the universe that are now separated by unimaginable distances could have been in very close proximity in the past. But in order for inflation to solve the horizon problem, the expansion would have to have taken place much faster than the speed of light. This may seem counterintuitive because of the universal speed limit of light, but that only applies to matter and energy within the universe. Space itself doesn't need to obey this speed limit. In fact, due to the rate of expansion of the universe, space today is still expanding faster than the speed of light, two galaxies more than 15 to 20 billion light-years apart would be moving away from each other faster than light. This means that the part of the universe you saw in Indonesia and the part you saw in Ecuador used to be much closer together. So close, in fact, that they could equilibrate and cause the haze of uniformity that we see when we look out. But of course, inflation is an extraordinary claim, for which extraordinary evidence is required, and definitive observational proof for this theory remains elusive. Despite this, indirect proof continues to pile up, which makes inflation an attractive theory. As we know, a universe that underwent inflation would be homogeneous, which on large scales ours is. An inflationary universe would also be flat, which ours appears to be. This flatness refers not to the number of dimensions, but instead to the effect of the density of matter and energy in the universe. Cosmologists can measure the shape of the universe in two independent ways. First, they can count up all the mass and energy in the universe and divide it by the critical energy density, the density at which the universe would be flat. And they can also measure it geometrically by measuring angles. On a positively curved sphere, like the Earth, a triangle drawn on the surface will have angles that add up to more than 180 degrees. The 3D geometry of the universe would be closed like this if it had more stuff in it. Eventually, gravity would pull everything together into a big crunch. In a universe with less stuff in it, expansion would continue forever and space would be hyperbolic. In a flat universe, straight lines and angles make sense. Triangles have angles that add up to 180 degrees. Results from both types of experiment show that what we have is a flat universe. Another plus point for inflation. And so this is strong evidence for the theory, but how then did inflation work to make the universe we see? One of almost perfect homogeneity, but not exactly perfect. Much, of course, can be gleaned from the universe's baby picture, the CMB, which shows us the after effects of very early fluctuations in density in the early universe. But anything before the CMB is obscured by the fact that everything was too hot for light to travel in straight lines. Excited electrons kept getting in the way, and inflation is supposed to have happened within a tiny fraction of a second after the birth of the universe. And so, there are nearly 380,000 years of physics that are hidden by the haze of 3-degree radiation. Where did these early fluctuations seen in the CMB come from? It's easy to point at a tree and explain that it grew from a seed. But where did the seed come from? Imagine a box with nothing in it. Close the lid so no light can get in. Take all the air out with a pump and seal it. Cool it down to absolute zero. Insulate it with lead so no radiation can penetrate. Is it empty? No. The universe is a fundamentally noisy place. There is no such thing as truly empty space. Even if there were no matter inside the box, space is always permeated by quantum fields with different values at different positions. One of these fields, the Higgs field, gives things mass. Another, the electromagnetic field, gives things charge and carries light. One of the big discoveries of early modern physics, by the likes of Heisenberg, Einstein and Planck, was the inherent noisiness of the universe. There is uncertainty at the smallest scales, which shows up as a faint buzz in the quantum fields. At the quantum level, even empty space is filled with quantum fields whose values are varying randomly. But why is this important for the large-scale structure of the universe? To answer that question, we have to go back to the very start. In the beginning, the observable universe was hot, dense, and tiny. The also tiny quantum fluctuations were buzzing along, with very small differences in the roiling patchwork of energy fields, as they do today. And then, suddenly and dramatically, inflation. The universe rapidly expanded by 26 orders of magnitude in a tiny fraction of a second. Changes this extreme are hard to describe. We don't have the words to properly conjure the scale of this explosion in our heads. 26 orders of magnitude is a grain of sand 1 millimeter across expanding to a septillion meters across. That's 100 million light years, something on the scale of Laniakea. And the violence of this detonation was staggering. In 10 to the minus 33 seconds, the observable universe went from microscopic to huge. For all intents and purposes, the expansion was instantaneous. And so this inflation amplified the quantum noise of the vacuum into genuine differences in density, thus giving gravity all it needed to work its attractive magic, gathering mass together into stars, galaxies, superclusters, and filaments. These variations would have been the first seeds, inconceivably tiny quantum fluctuations, the forefathers of vast intergalactic filaments, many millions of light years in length, tiny acorns growing into vast forests. But that is not the end of the story. After inflation was complete, the universe continued to expand and cool down, but it remained extremely hot and dense. If the large-scale structure of the universe were purely shaped by the expansion of quantum fluctuations, you would expect everything to be distributed fairly randomly. Indeed, if you look at a population of galaxies and ask how far each galaxy is from each other galaxy in the population, you should see a simple relationship and regular clustering. Galaxies would tend to be fairly close together because of the clumping effect of gravity, and so you should be less and less likely to find two galaxies separated by larger distances. And yet this is not what astronomers see. When they do this kind of analysis, they observe one peak for galaxies that are close together, as expected, and another one for a separation of about 150 megaparsecs. What explains this overabundance at what seems like an arbitrary distance? The answer lies in what's known as baryon acoustic oscillations, galaxy dwarfing sound waves. For hundreds of thousands of years after the Big Bang, it was too hot for atomic nuclei to capture electrons. The universe was a sea of charged particles, and photons of light couldn't travel in straight lines. They would get bounced around, scattering in every direction until they hit the next stray electron. As it cooled, some of the regions that were more dense would pull more and more stuff in. But photons exert a pressure when they get too close together, and this pressure would push out, carrying some matter with it. And this is where dark matter entered the picture. Dark matter outweighs regular matter in the universe by 5 times. It was and remains the dominant gravitational force in our universe. The cosmic web of stars, galaxies, and filaments is really a web of dark matter, with regular matter tagging along. It accounts for something like 85% of the gravity in the universe, so everything from galaxy formation to star clustering and gravitational lensing is dictated by its properties. And yet we still don't know what it really is. What we do know is that dark matter interacts gravitationally, but doesn't seem to be affected by electromagnetism, such as light, or the other fundamental forces. So, as clumps of density began to form in the early universe, the photons would eventually get squeezed so much that they would burst out in a ferocious wave of plasma, carrying some regular matter, also known as baryons, but leaving the dark matter behind in the center. Imagine a pebble dropped in a pool. There is a central splash and then concentric rings of ripples. Now imagine millions of pebbles dropped at slightly different times. It would create a complex jumble of splashes, ripples, and regions where the rings interacted. This was the state of the universe after inflation. But the universe was cooling. And once it reached 3000 Kelvin, protons were able to capture electrons and the phase changed. Instead of a bubbling, opaque plasma, it became a transparent gas. The moment the universe became transparent, the cosmic microwave background radiation escaped, and the expanding rings suddenly stopped because the photons that were carrying the matter were no longer coupled with that matter. The photons rushed off in a straight line, leaving the ring frozen at the distance it had reached. and that distance is 150 megaparsecs, exactly where we see the second bump in the graph of galaxy separations. This is one of the ways that cosmologists can see past the CMB, by deciphering the patterns in its seemingly random distribution. Dark matter is central to this story, and indeed the structuring of the universe that followed. In fact, in a lot of ways, dark matter is the true main character in the narrative of the universe, and yet lay almost completely undetected until the mid-20th century. Back in 1933, a young and ambitious Swiss astronomer named Fritz Zwicky noticed something odd about the speed of stars in a galaxy. He observed that two independent measures of the mass of a cluster of galaxies weren't lining up. If he counted up all the stars and added their mass, he got a number 10 times less than if he instead calculated the mass by looking at the speeds of the galaxies in the cluster. He thus concluded that there must be an enormous amount of unseen mass. However, it would be more than 30 years before further evidence would come to light, as pioneering astronomer Vera Rubin set her sights on spiral galaxies. In predicting the motions of stars around the center of galaxies, astronomers had always made 3 assumptions. 1. Gravity depends on distance and mass. The closer and more massive two objects are, the stronger gravity acts on them. 2. Spiral galaxies have most of their stars in the very bright central regions. And 3. Stars on the edge of galaxies would have less gravity acting on them and would travel more slowly. This is analogous to our own solar system. Most of the mass is contained in the Sun, so the close planets like Mercury, Venus and Earth travel much faster than the gas giants Saturn, Uranus and Neptune. So imagine Vera Rubin's surprise when she observed the speeds of stars in nearby spiral galaxies. She found the relationship between speed and distance traced a straight line in her graph. Instead of acting like the solar system, the stars on the edges of spiral galaxies traveled just as fast as those in their cores. And so there was a fourth, hidden assumption that astronomers were making, which Rubin made explicit. While it was true that spiral galaxies have most of their stars in the central regions, stars don't account for most of the mass. In order to account for this increased speed, normal matter, stars, dust, nebulae, could only account for 15% of the total matter in the universe. So what was this dark matter? The leading theory currently is WIMPs, weakly interacting massive particles. These would be elementary particles like protons or neutrons, but would have peculiar properties. Unlike protons, which have a charge and interact with light, these WIMPs would be invisible and only interact with gravity. They would also need to be much heavier or much more numerous in order to make up for the missing mass in the universe. Today, we know that all galaxies except some dwarf galaxies have larger halos of dark matter surrounding them. Scientists estimate that the Milky Way's halo could extend up to 15 times further than the matter we can see. Searches for these particles at particle colliders like the Large Hadron Collider in Switzerland, at giant vats of noble gases in Antarctica and other places have so far come up without definitive proof for the WIMP theory. But scientists are hopeful, as dark matter explains so much about the large-scale structure of the universe. It makes everything make sense. The echoes of baryonic shockwaves, the speeds of galaxies, and the patterns of clustering. In the growth of structure across the universe, normal matter, what we see and what we are, is only really a bit player. The main role in building the universe goes to this mysterious, invisible stuff. And so, from minuscule quantum fluctuations to galaxy dwarfing sound waves and finally vast tides of dark matter, our webbed universe was born. Problem solved? Not quite. There are further structural mysteries out there, mysteries we haven't even begun to unravel. We are all moving in the same direction. We're spinning on the Earth, which is revolving around the Sun, which is spiraling around the galaxy, which itself has motion. But zooming much further out, all the galaxies around us in Laniakea are pulled towards the same point in space. We are all moving in the same direction. But where are we going? As scientists studied the CMB for the first time, it became clear that our local group of galaxies was not stationary. It was moving relative to the CMB. In fact, we are rushing at around 1,000 kilometers a second towards a point 250 million light-years away. And this point was dubbed the Great Attractor. But what was there? Why this particular point and not somewhere else? If, according to the Copernican principle, no point in space is more special than any other, why should so much mass move towards this one spot? We didn't know then, and we still aren't sure. One challenge was that whatever we were heading for was very hard to observe because we had to look through the center of our own galaxy, an area known as the Zone of Avoidance, and one through which our view is obscured by interstellar dust. But we could see through it with X-rays, and this method revealed a group of galaxies known as the Noma Cluster. But this alone wasn't enough to cover the flow of galaxies, and so scientists watched the Great Attractor and came to a remarkable conclusion. It is itself in motion towards a greater source of mass. 650 million light-years away lingered a vast supercluster, the largest for 1 billion light-years. Known as the Shapley Supercluster, this Leviathan contains the mass of nearly 10,000 Milky Ways. But that wasn't the end. In 2017, researchers proposed a further element. Dubbed the Dipole Repeller, it is a large void in almost the exact opposite direction to the Shapley Supercluster. Whereas Shapley pulls, this area of space doesn't literally repel, but its underdensity means it can't overcome more powerful gravitational forces. And we are sandwiched in the middle of this massive stellar flow, almost 1 billion light-years across. Though this may seem unbeatably large, this is only the beginning of the structural oddities that appear in the large-scale mapping of the cosmos. One long-standing mystery that came to light in the early 2000s was related to the assumed homogeneity of our universe. The issue is fairly simple. If you divide the sphere of the CMB into 4 or 8, the top right is on average hotter than the bottom left. This effect disappears if you divide the sky into more and more pieces, but for the quadrupole and the octopole, the angle of the line between the hot part and the cold part matches almost exactly with the plane of our solar system. This is a result so odd that astronomers have named it the axis of evil because it threatens to break our most fundamental ideas about the universe. Why would the background of the universe be aligned with our solar system? We don't know. Nobody does. The chief scientist of the WMAP telescope, Charles Bennett, thinks it must be a coincidence. I do think that there is a bit of a psychological effect. People want to find unusual things. But even with new data from the Planck telescope, the effect is reproduced. In the words of Dominik Schwarz from the University of Bielefeld in Germany, for a long time, part of the community was hoping that this would go away. But it hasn't. It is still totally unexplained. We understand so much about our physical world. We can shoot satellites into the sky to take baby pictures of the universe and use these images to rewind the cosmos back to its first moments. Between general relativity and the standard model of particle physics, we think we have it all figured out. But there is much we do not know. Of course, in order to have structure in the universe, first, the universe must begin. So how did we get our start? What set off inflation? The answer to this question may be hidden in the patterns of the universe's largest structures, One idea is that in the primordial universe there is a roiling sea of dense vacuum energy, and it just takes something to set off an inflationary bubble, which then grows into a universe. But there's nothing saying ours was the only inflationary bubble. Perhaps another universe formed nearby, just on the other side of the CMB, and if it went through inflation, it might collide with us. So this is one big mystery that the CMB may yet hold the answer to. Great spots in the sky resulting from collisions with other bubble universes. We haven't seen anything yet, but even the possibility of evidence for multiverse theories is so sparse that merely a method to find a glimmer of proof is enough to excite scientists. Where are you? The Observable Universe, Laniakea, Virgo Supercluster, Local Group, Milky Way, Orion Arm, Local Cavity, Local Interstellar Cloud, Oort Cloud, Solar System, Earth. At every scale, there is structure, there is order. This structure is governed by simple principles: gravity, which is dominated by dark matter, and expansion, which is now driven by dark energy, but which at one stage was the result of inflation. And yet these basic principles turn matter and energy into huge, beautiful structures, bathed in the warm glow of the cosmic microwave background radiation. Copernicus, Shapley, Zwicky, Rubin, Zeldovich, Peebles, Gott. All of these scientists and the teams that supported them have brought us this far in uncovering its secrets. And yet, despite all that we know, there are still mysteries out there, written in the stars. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think. Thanks for watching, and we'll see you next time.